All right. Well, hey, welcome to May. We are now a third of the way through the quarter. We are flying by. Um, anyway, today's plan is to pretty much pick up where we left off. Excuse me. We're going to talk about um, linear second order homogeneous differential equations with constant coefficients. We're going to continue our discussion. We're kind of in the middle of there. And then we'll start turning our attention to, all right, well, what if they're not homogeneous, and some general theories behind that and all that. So that's my plan. But before I do that, let me turn it over to you guys. Are there any homework questions you'd like to look at? Anything we've talked about that you're curious about?
We go on number 10 of 4.3.
All right. 4.3, number 10, which looks like Ralph also says he would like. He'd like to look at 5.1, number 14. Any others? All right, well, then let's go ahead and hop over and take a look at those. We'll look at the one from 4.3 first. Share my screen. All right, so an object weighing 256 pounds is dropped from rest in a medium that exerts a resistive force with magnitude proportional to the square root, or sorry, to the square of the speed. The magnitude of the resisting force is 1 pound when the speed is 4 feet per second. Find V, and then find the terminal velocity of this object. Okay, so let me just write down the important information here. All right, so let's go to Whiteboard. All right, well, let's start with what we're told about the resistive force and all that. So we've got our object that's falling. So there's going to be gravity pulling us this way, and then there's going to be the resistive force, I'll just call it drag, that's going in this direction. So we're going to get mass times acceleration is equal to gravity, so mg minus kv squared. So we're going to go with a kv squared because it said it's proportional to the square of the velocity. And we'll just throw a k in there because we need to have a k. All right, so at this point, how are we doing? So far, so good?
Yeah.
Okay. So now let's start putting in what we know. So we're told that this thing weighs 256 pounds. Well, of course, we're in this world. 256 pounds, this actually is mg. Pounds are not mass, pounds are force. So that actually is going to equal 256. So if I kind of rewrite this, I'll put all the v stuff onto the one side. We'll change the a to a v prime. That's going to equal 256. All right, now we are going to need to find the mass. And so the mass is going to be 256 divided by g. And in our stupid system, g is 32 feet per second squared. So that's going to be 246 over 32, which what goes into that? 4 goes into that? No. 4 does not go into that. 2 does, though. So 123/16, I believe. Oh, thank you. 256. Nice catch. Then all kinds of lovely stuff cancels. Thank you for that, Ralph. Because then 32 actually goes in evenly. That goes in 8 times. All right, so just so you guys know, the unit here, those are slugs. So the mass of this object is 8 slugs. Okay. All right, well, that's getting us closer here. Actually, hold on, erase that 8, looks a little bit funky. So we now have 8 v prime plus kv squared equals 256. So we're getting closer. So now we got to get the k. But this is where we had a little more information, right? We were told that when v is 4, the drag was equal to 1 pound. So that means that resistive force, kv squared, so k times 4 squared, is going to equal 1. So that gives us k equals 1/16. All right, so we'll put that in.
I think it was when b is 2 or -2, right?
Let me double check. No, it's when v is 4. Let me show you real quick. Right, so the resisting force is 1 pound when the magnitude of v is 4 feet per second.
Okay, makes sense.
Okay, so I think we're good there, but thank you for checking that. Those are definitely the kinds of things that I miss. All right, so there you go. There's our differential equation. I'm going to multiply everything by 16 just because I want to get rid of the fraction. So we're going to get 128 v prime plus v squared. And then that's going to equal, oh goodness.
4608.
Thank you. No, can't be. 256 times 16.
4096. I did 18 on accident.
It's, as I'd say, it's got to end in a 6. So. All right. So there's our differential equation. So this is the guy that we're going to have to solve. All right. So, yeah, how are we going to solve that?
Well, we can solve the homogeneous, I guess.
Can we? I mean, this is a v squared.
Oh yeah.
So notice that it's not linear.
So separable.
Yeah, this one's separable. If we just do a little bit, we get 128 v prime equals 4096 minus v squared. So we get 128 over 4096 minus v squared equals 1. So that one's separable. And now we can integrate both sides. All right, so I'm just gonna crack out my trusty T89 because I'm definitely way too lazy to try to do this one. This is one where we would have to do a partial fractions because we've got the 4096 minus v squared is a difference of squares. So you could factor that thing, create your partial fractions. And whoops, that's not the right answer. Okay, so here's what my T89 gives us. We're going to get the natural log. Go back a page. So we get the natural log of v plus 64 over v. Oh, no, hold on. Let me do it the other way here. 64 plus v over 64 minus v equals t plus c. All right, so then we run the hook. And I'm officially bored with this one. You guys can work your way to solving it for v, but you see exactly what you need to do at this point. But the one thing we can do is actually take care of that c, because if we go back and look at it, let's see what it said. I think they gave us initial. The object weighing 256 is dropped from rest. Okay, so if it's dropped from rest, that means that v is equal to 0 when t is equal to 0. So if you put that in, you get 64 over 64 equals c e to the 0. So c equals 1. So that's actually equal to 1 right there, which makes it a little bit easier actually to end up solving it for v. Okay, so that gets us our v, and then if we want a position, we're just going to integrate that thing. All right, so how's that for the first part of this question? We good at this point?
Yeah.
No? All right, so now the last thing we have to do, because it also said figure out what the terminal velocity is. And it turns out that we don't need to actually have the whole thing solved to do that. Do you remember what we do to find terminal velocity?
Take the limit as t goes to infinity.
Okay, so we take a limit as t goes to infinity of our function for v, but we don't have that. Does anyone remember what you can do with the differential equation to figure that out?
Probably when b is 0.
It's going to be when the v prime is 0. Because at that point, we're not changing our speed. We reached our maximum velocity, and that's where we're staying. So v prime is equal to 0. So we can actually answer that just by plugging 0 in. So that v is going to be 4096 is going to be v squared. So what is that? $64. So as we get closer to infinity, our velocity is going to get closer and closer to 64. All right, so how was that one? Is that all right for 5.1, or sorry, 4.3 number 10, specifically to you guys that were asking for it?
Yeah, that's nice. That's better.
All right. Anyway, this part should be pretty easy to cruise through on your own. Okay, so let's go look at the other one from 5.1. It was number 14. So go here. All right. So for this one, it says, use the method suggested in exercise 9 to find a second solution that isn't a constant multiple of the other solution. All right, now, I don't know what example 9 is. I'm not going to go back and, or exercise 9. Well, might as well, it's right here. All right, it says that show if, so y1 is a solution to the homogeneous. Then show that we can find y2 equaling uy1, where u prime is equal to this stuff. Okay, so we might as well make use of that, seeing it's right there and everything. So that k, that is the constant that comes from the Wronskian stuff. Remember when we use Abel's theorem, we know that the Wronskian, we're off by at most a constant. Well, that's what that k is. But we're going to use this to figure out what our y2 is equal to. So I'm almost there, writing down everything that we need. All right. Let me go ahead and go to the whiteboard. We'll clear all this stuff and start fresh. All right. So again, here's what we know. We have a differential equation that's x y double prime minus, or sorry, x squared y double prime minus xy prime plus y equals 0. And we're told that one of the solutions is x. Now, I want you just to notice that that definitely does work. If y is equal to x, y prime is 1, y double prime is 0. You get 0 minus x plus x, which equals 0. All right. So I think what I'm going to do, actually, is just show you, okay, we're going to take the method all the way through. And so what we're going to do is the same thing that we've done a million times, where we go, all right, I want something else as a solution, and I want it to be a multiple of y1. And let's see what that's going to force it to be. Okay, so y2 prime is going to be u prime x plus u. Y2 double prime is going to be u double prime x plus 2u prime. I don't need another plus there. So the 2u prime, one of them came from this, the product rule in the first piece, and the other came from the u. All right, so far so good. So now let's plug these in. So we're going to get x squared times u double prime x plus 2u prime minus x times u prime x plus u plus u times x. And we need that to equal 0. So we get u double prime x cubed plus 2x squared u prime minus x squared u prime minus xu plus ux. All kinds of lovely stuff cancels. And we can combine some other stuff. So we get x cubed u double prime plus x squared u prime equals 0. So let's divide everything by x squared just to make life easier. So we get x u double prime plus u prime equals 0. And I'm going to change these guys because I know seeing them as u's and all that you may not like. Let's call it, say, v is u prime. So then u double prime is v prime. So this becomes x v prime plus v equals 0. And this guy's separable. So we have x v prime equals minus v. V prime over v is equal to minus 1 over x. And now we can integrate those guys. So we get the natural log of v is equal to the negative natural log of x plus c. So v is going to equal c over x. Because that minus 1 comes in, we get x to the minus 1, the e and the natural log cancel, so we get x to the minus 1. But now, let's go back here. We know v is equal to u prime. So we just have to integrate again. And we get u is equal to c1, we'll call that guy c1, times the natural log of x plus c2. And remember what we were doing with u, if you come back over here. We can now put this together to get that y2 is equal to all of this times x. But this piece right here, we can ignore it. Why can we ignore that? I'll give you a hint. Remember what y1 was? It was x. So that c2x is actually part of the part that's spanned by y1. So what I would do if I just wanted a y2, I'm going to pick x natural log of x. And so then I can piece those two together. And so what my y will look like is c1x plus c2x log x, which was exactly the whole thing that we found over there. So this trick, this integrating factor trick, oh my God, we use it all the time. It is so useful when you know a solution. So this one, y equal x works, but then so does x log x. And you can check that. I'll trust you to check it on your own, take its derivative, its second derivative, plug it into the differential equation, and you'll see that you do get 0. But I want to just go back and see what we had to answer, make sure we answered everything here. Find a second solution y2 that isn't a constant multiple of y1. Okay, well, we just found it. And yeah, they used a different method. I don't expect that you necessarily use number 9. You can if you want. But this is a really handy trick for sure. All right, so was that better for whatever number this was, number 13? Oh, all right, thanks for the thumbs up, Ralph, appreciate it. All right, so yeah, there you go. So I think the moral of the story here is with differential equations, expect the same thing to keep coming up. Like how many times have we done this integrating factor trick? Tons. It's not going away. And in fact, that's what we're going to start with today. Is you may remember when we were doing what we ended up with last time when we were looking at the linear second order homogeneous with constant coefficients. What we saw there was that we had to create that polynomial, and it was the roots of the polynomial gave us the fundamental set. But we ran into that situation where we only found one root. It was a repeated root, and we had to find a second function. And so we did that trick of integrating factor with our specific example. But I want to start by doing it generically. Let's do that generically for one of these things so that we can see what we end up getting, like what it kind of forces the form to be, because there is a form for your second function in that situation. All right. So let me hop up to the whiteboard and we'll continue our discussion on this. All right, so I just want to remind you real quick where we got last time. So we're looking at linear, second order, homogeneous with constant coefficients. So a lot of qualifiers, right? But they were the ones that can be written like this, where A, B, and C are all constants. So what we did, the process for these, at least what we learned last time, is that you just create what we call the characteristic polynomial. Which is going to be AR squared plus BR plus C equal to 0. And we find the solutions. And the first case we saw was when you get two real solutions. Then we had y1 equals e to the r1t, and y2 equals e to the r2t. So those were the, like, that's the stupid, crazy, easy ones, right? Like, honestly, these are the ones that you don't have to think about. For example, would be like y double prime minus 4y prime minus 5y equals 0. So you make your polynomial. In this case, it's going to be r squared minus 4r minus 5. That factors to minus 5 and plus 1. And so we get y1 equals e to the 5t, y2 equals e to the minus t. And then once we have our fundamental set, it allows us to get our solution. So the solution here, generic solution. So there's the general solution to that differential equation. So those are the ones that we like. We get 2 different roots and we're done. But we were in the middle of case number 2, which is when we get 1 repeated root. And in that case, we saw that the one of them was the e to the r1t. But the question is, what is the second? And I know that we did a specific one. And that specific one, what did we find? It was, I think it was t times that guy. Right, so the other one was like, I forget what our example was, but it was like e to the 3t, and then the other one was t e to the 3t. But what I'd really like to do, and that's what we're going to do right now, is develop what that second one has to look like. What does that second form have to be? Is there a pattern so that we don't have to do that integrating factor every single time? Okay, so let's see if we can tackle that. Let's see if we can find out in general what the second and the fundamental set are going to be. So the way we're going to attack this is we're just going to go with saying that we factored one of these guys. So we've got AR squared plus BR plus C equals 0. So let's start with what has to be true for this to have just one solution. So go back to your quadratic, and you get one solution when b squared minus 4ac is equal to 0. Because that's the plus or minus piece, then we get plus or minus 0. So that actually gives us a solution of r equals negative b over 2a. Okay, so we know that this is what the structure has to be. But we can also think of it as, if we call this, let's say, R1, because that's our solution, we can think that this polynomial has to factor as R minus R1 times R minus R1. So that actually tells us a little bit about the characteristic polynomial, because if I multiply this out, I get r squared minus 2r1 times r plus r1 squared. So our original differential equation is going to have to be of the form, or be made into the form, y double prime minus 2r1 times y prime plus r1 squared times y equals 0. So notice what I'm doing is I'm just reverse engineering. Instead of starting with my differential equation, finding my root, I'm starting with my root, going back to my differential equation. Okay, so it has to be at least, we have to be able to write it in this form. There is the possibility that it doesn't start in that form, but we can get there by dividing. Okay, so now we're going to play the same trick that we've always played. We're going to look for a y2 that's going to equal u times y1, which in this case is going to be u times e to the r1t. Because we already know we're going to get that e to the r1t. So the question is, what's the other one look like? Okay, so let's get derivatives. y2 prime. Well, it's going to be u prime e to the r1t plus r1 u times e to the r1t. So that's just good old product rule. And then when we differentiate a second time, we're going to get u double prime e to the r1t. We're going to get plus 2 u prime r1 e to the r1t. There's going to be one from each of these. And then plus r1 squared u e to the r1t. I know it's ugly, but watch how fast this simplifies when we actually put this back into the differential equation, right? So we're going to take all of this and fire it back in here because we know that we're going to need this to equal 0, and this is what our differential equation looks like. Okay, so we get the y double prime, we get all that stuff. We're then going to subtract 2r1 times this other thing. So I'm going to stack them up. So we get a minus 2 u1r1 e to the r1t. And then minus 2 r1 squared u e to the r1t. Okay, so that's the minus 2 times this. And then I'm going to add to this r1 squared times y2. So r1 squared u e to the r1t. So here's our y double prime minus 2y prime, or 2r1 y prime, plus r1 squared y. All right, well, these cancel. These cancel. And all I'm left with is u double prime e to the r1t has to equal 0. Well, e to the r1t can't equal 0, so that means u double prime equals 0. So I need a function whose second derivative is 0. How about we pick t? All right, so when we did it last time, we ran into, we need our multiplier to be t. Now we see that it's true no matter what that first root is. So when you're in this situation where you get just the one root, obviously the first function is going to be e to the rt. The second function is going to be t times. Yay. Okay, this is actually good news because we've solved every single one of these ever. All right, so repeated root, no big deal. But there's actually a third possibility. When you solve a quadratic, you can get two real solutions. You can get the one solution that's repeated. But the other possibility is that you get the two complex solutions. And so the question is, what do we do then? Because these would be the kind, you know, where when you solve for your roots, you get 1 plus or minus I, right? Something like that. And now we have a bit of an issue. We're getting complex things in there, and we're dealing with real valued functions. How do we deal with that? What do we do? Well, to deal with the complex roots, I need to show you something called Euler's formula. And you may have seen Euler's formula. I don't know if you have or not, but I'm going to show it to you just so you can see what it looks like. So you can see what we're going to be doing. Okay, well, let me back up just a second. And let's just say when we solve our characteristic polynomial, let's say that we get complex roots. So I'm going to use the letters that they use in the book. They use the Greek letters lambda and omega. But we're going to get a real part, lambda, and we're going to get an imaginary part, the omega I. But they're always complex conjugates. That is one nice thing about these, is that they're going to be identical, with the exception of a plus or minus on the imaginary piece. All right, so what that would suggest this suggests solutions of e to the lambda plus omega I times t and e to the lambda minus omega I times t. Right? The same idea as before, where we're just putting those roots in on our powers of e. But at this point, it's very, very okay to be like, what the hell does that even mean? Right? What does that actually mean? What kind of form are we getting? The e to the lambda piece, yeah, that's easy. It's just e to the lambda. But what is e to the I? What does that even do? All right, well, let me show you Euler's formula. And this is going to bring back power series. So do you remember your power series for e to the x? Anyone remember what the form was for the power series for e to the x? And it's okay if the answer is no.
I remember it was divided by n factorial, I think.
Okay, good. That's exactly right, Victor. On the bottom is an n factorial. You're halfway there.
And probably x to the n.
Yep. All right. So if you have any power series questions, go ask Victor, because evidently he remembers them all. At least he was able to get that. Okay, so e to the x is equal to x to the n over n factorial. So here's what we're going to do. Let's look at what e to the it is. Okay. So what we're going to do is we're going to plug into this power series it. I'm not worrying about the omega, because the omega part doesn't matter, right? I mean, that it will matter, but it's just going to be a constant number that comes from whatever the roots are. The important piece of this is the I times t, because I can't get rid of either of those. I is I, and t, that's obviously the variable that we need in here. All right, well, let me write out the first few of these. So if we were actually just plug this in and calculate, the first term is going to be a 1. Then we're going to get I. Then we're going to get a minus, or sorry, T. Yeah, IT. Sorry, yeah, IT. Then the next one is going to be minus T squared over 2 factorial. And it's a minus because there's an I squared. And the I squared turns into a minus 1. The next one's going to be a minus IT cubed over 3 factorial. Then a plus T to the 4th over 4 factorial. And then a plus IT to the 5th over 5 factorial. And so on down the line. So this one actually goes plus, plus, minus, minus, plus, plus, minus, minus, because of the powers of I. And every other one has an I. So what I'm going to do is I'm actually going to separate these out into the pieces that are real and the parts that are imaginary. So the real parts we're going to get 1 minus T squared over 2 factorial plus T to the 4th over 4 factorial minus T to the 6th over 6 factorial, and so on. And then the other parts, if I factor out the I get T minus T cubed over 3 factorial plus T to the 5th over 5 factorial, so on down the line. All right, so I'm curious if anybody recognizes the power series that's in the first parentheses. The one with all the even powers of n, or yeah, even powers.
I remember things related to even powers was like sine or cosine.
Okay, good. That is either sine or cosine, and it turns out that's cosine. Best way to remember that is cosine's an even function. So it has to be made up of even degree terms in the power series. This other one that has all the odds, that's sine. Okay, so check this out. This is kind of cool. E to the IT is equal to cosine t plus I sine of t. And this is Euler's formula. That's the name of this. Because Leonhard Euler was the one who figured this out. Okay, so actually now we know what to do with these i's. They're actually going to turn themselves into sines and cosines. All right, so let me just show you how this plays out. Y1, if we just kind of break this down, it's going to be e to the lambda t time or plus omega I t, which is e to the lambda t times e to the I omega t. All right, well, the e to the I omega t, it actually turns this into cosine of omega t plus I sine of omega t. The omega, while it wasn't in here, when I did e to the IT, It's just going to be on all of these things. So this will be omega t quantity squared, omega t to the fourth, omega t to the sixth, which makes it a cosine of omega t. So that's what y1 is going to look like. And then y2 is going to be virtually the same. It just needs a minus omega t in each of those, right? Because it's a minus omega it. But we know what happens with minus signs in trig functions. In cosine, it just goes away. And on sine, we can pull it out front. So it looks like that. So again, the only difference in these two is the plus or minus sign on the I. All right, so this should start making you feel a little bit better, because we no longer have e raised to an imaginary number. But there's still a bit of an issue. What's still not so nice about these?
We have an I.
Yeah, there's still an I. Not one I. Okay, well, let's think about what we're going to do to form our solution, right? We're going to have y equals c1 times the first plus c2 times the second. Okay, so those c's, though, can be like literally anything, because they're completely arbitrary. And in fact, those c's could even have imaginary numbers in them. All we need to do is make sure that the C1 and C2 are such that when they're combined, give us real coefficients for both sine and cosine, and that we totally can do. So we're going to go ahead and distribute all that stuff through, and this is what y is going to look like. We're going to have e to the lambda t, and then I'm going to change the c's so that we just write them as C1 times cosine of omega t plus C2 sine of omega t. And we're going to go ahead and put a box around this, because this is what our solution is going to be when the characteristic polynomial gives us complex roots. No, let me write imaginary. Right? So if they're imaginary, this is what we're going to get. So that's our third and final case. So we now know exactly what's going to happen anytime we have linear second order homogeneous with constant coefficients. We're going to make that polynomial. We're going to find its roots, and then depending on what its roots are, we're going to do whichever of the three cases. All right, so this is the least nice one, but it's totally going to be what we need and how we're going to get the solution. So let me show you an example using complex roots. These guys that are going to lead to some i's. Just so you can see kind of how easy it actually is. All right, so let's look at this guy. Let's say we've got y double prime plus 25y equals 0. So we make our polynomial, and we get r squared plus 25 equals 0. This one, I'm just going to go ahead and solve for r. So r is plus or minus the square root of negative 25, which is plus or minus 5i. So in the context of our formula, we have lambda is 0. There is no real part to it. So we're going to put 0 in for lambda. And then omega is going to be 5. So putting that into this formula over here tells us that what we're going to get is y equals e to the 0t times c1 cosine of 5t plus c2 sine of 5t. Well, e to the 0 is 1, so that just goes away. And so there is the general solution to this differential equation. It's y equals c1 cosine of 5t plus c2 sine of 5t. And if we wanted to like get back into the language we were talking about before with fundamental set and all that, here are your two functions. Y1 is cosine of 5t, and y2 is sine of 5t. Those are a linearly independent set of functions that give us all possible solutions. And it's really easy to check them, right? Like, let's just check that sine of 5t real quick against this differential equation. So if y is equal to sine of 5t, then y prime is 5 cosine of 5t. Y double prime is minus 25 sine of 5t. Put these guys in over here, and you see really fast, yep, they are a solution. Same thing is true for the cosine of 5t. And because they're not linear multiples of each other, they are linearly independent set. Therefore, they form a fundamental set of solutions. All right, well, you may remember that when we went back to the beginning, when we were talking about what are the functions, what are they going to have to look like to be solutions? We ran into exponentials and trig on our list, and now we see why. They absolutely will be solutions, again, depending upon the structure of the very original differential equation. Okay, so before we do a few more of these and practice a few more, any questions about the derivations? How we got those? Hopefully you're good with the integrating factor trick for the repeated root. It's super nice that it's always t. And the sine and cosine one I know is weird because we're making use of that Euler's formula. But you can trust me on it. It definitely works. All right, well, let's do a couple. Let's just practice a few more here, see if we can figure out what the solutions look like. And we'll even throw in some initial values. All right, but I'm not going to tell you ahead of time which of the three scenarios we're in. Okay, we're just going to take them as they come, and we'll see what we find as our solutions. Right. So here's our first one. Let's go with 4y double prime plus 4y prime plus y equals 0. And let's even make it an initial condition problem, initial value problem. So we have y of 2 equals 1, and y prime of 2 is equal to 0. So let's see if we can find our solution. So first things first, make your polynomial. 4r squared plus 4r plus 1 equals 0. All right, so what are the solutions to this one? Well, there's one factors. So we got r equals minus 1/2. But it only shows up that one time. So this is the case where we've got repeated roots. So our y is going to equal c1 times e to the minus 1/2 t plus c2. And what's the other function?
Same, but with a t in front.
Good. So it'll be t e to the minus 1/2 t. All right, so now let's use our initial conditions to figure out what C1 and C2 are. We are going to need Y1 prime, or Y prime, so let's get that real quick. So it'll be a minus 1/2 C1 e to the minus 1/2 t plus C2 e to the minus 1/2 t minus 1/2 C2 t e to the minus 1/2 t. That was just the product rule on that second piece. So let's see what our initial conditions tell us. The y of 2 equaling 1 gives us 1 equals c1 e to the minus 1 plus 2 c2 e to the minus 1. So I think this will be a little bit easier to see if we just multiply everything by e. So c1 plus 2c2 has to equal e. And then from the derivative, you get 0 equals minus 1/2 c1 e to the minus 1 plus c2 e to the minus 1 minus, well, I plug in a 2 times 1/2, of course, is 1. So we get minus 1 c2 e to the minus 1. And those guys actually cancel each other out. All right, so this guy gives us c1 equals 0. We fire that up into here. We get c2 equals 1/2 e. So here is our solution to this differential equation then. It's going to be y equals 1/2 e t, 1/2 e times, not to, times t e to the minus 1/2 t. And we could actually combine that. So 1/2 t e to the 1 minus 1/2 t, using the rules of exponents. So there is the function. This is the function that satisfies those conditions. So it passes through the point 2, 1 and is actually flat temporarily at that point. And it satisfies this differential equation. All right, so hopefully you're seeing it. I mean, it's very systematic. We're going to do exactly the same thing for this next one. We're going to do exactly the same thing. It's just not going to be a surprise to you that I'm going to make it so that we get a different form for our derivative. All right, so let's try this one. Let's say we've got y double prime plus y prime plus y equals 0. And this one, we won't make an initial condition. All right, well, we're going to start exactly the same way. Let's begin by creating our polynomial. So we have r squared plus r plus 1 equals 0. This one does not factor. So if you go to the quadratic formula, you get -1 plus or minus the square root of 1 minus 4 all over 2. So we get -1 plus or minus the square root of -3 all over 2, which is -1/2 plus or minus √3 over 2 times I. And I am going to split it into the two pieces because I want to be able to recognize my real part and my complex part. So when you run into something like this, make sure you split it apart. All right, so what we know then is here, lambda is -1/2 and omega is √3 over 2. So we can put that together to get our solution set of y equals e to the -1/2 t times c1 cosine of √3 over 2t plus c2 sine of √3 over 2t. And so there's the general solution to this differential equation. All right, so what do you guys think at this point? Are you bored?
Very different than linear.
Okay, yes, it's definitely very different than linear. But it's the same thing every time. Make the polynomial, find the roots, use the roots to tell you what the answer is. Trust me, you're not gonna have to do very many of these for you to be like, ah, okay, it's just another one of these functions. But I want to point something out here, because Victor just said it's very different than linear, except it's not. Check this out. Let's go to our first order, I think is where you meant to go. So think about this. What if it's a first order linear with constant coefficients? So we're going to have ay prime plus by equals 0. All right. Now, think about this can end up looking like, this is going to be y prime plus cy equals 0. And I want to think about how we solve that. Remember what we did? It was e to the negative integral. Yeah, let me just do this. Let me call it a. Minus a. So this was e to the minus at plus c. So y was equal to c e to the minus at. Right? That was the solution to the homogeneous of this form. Well, what if we thought about this as the polynomial kind of deal? If we make a characteristic polynomial, that's going to be r plus a equals 0. If you solve this, you get r equals negative a, which would suggest that y1 is c1 e to the negative at. Okay, this is when you go, you son of a. Yeah, we could have been doing this the whole time. And like linear ones are no big deal with constant coefficients, because all you have to do is take whatever that is, once you get it as y prime all by itself, you take the coefficient on y, e to the negative of that times t, and you're done. So while it feels very different than what we did for linear, it's actually the same. It's just requiring more steps because we need more than one solution. And solutions to linear polynomials are always easy. There are no options. There's always just the one answer. So turns out it is the same thing. And now that you know this, it can definitely help you with the, like if you were to go back to the stuff from chapter 2, when we first did the linear first order stuff, the ones with constant coefficients, man, you can blow through those now. You don't even have to think about them once you do this process a few times. Okay, but I promise you that the more you practice these, the easier they're going to come, because it really is just create the polynomial, find the zeros, and then figure out what your form is. All right, but this is very restricted. Linear second order homogeneous with constant coefficients. So we have to start expanding. What about things that aren't linear second order homogeneous with constant coefficients? So what we're going to turn our attention to next is, what about non-homogeneous? Let's just change that. We're still going to go with constant coefficients. What if it's non-homogeneous? Okay, well, to help us a little bit, let's just talk about general. Right, so general non-homogeneous versus homogeneous. All right, let's just do general non-homogeneous. So what are we going to do when they're non-homogeneous? So we're basically saying now we're going to have y double prime plus p of x times y prime plus q of x times y, but now it's going to equal some other function. We'll call it f of x. All right, well, here's your first theorem. It's going to be theorem number 1. Right? And what it says is that if P, Q, and F are all continuous in an interval containing, let's call it x naught, then the initial value problem with y of x naught equals k naught and y prime of x naught equals k1 as a unique solution. So these K naught and K1, those are just whatever the initial values are equal to. All right. So when we've got non-homogeneous, as long as these three pieces are all continuous in an interval that contains your starting point, you're guaranteed a unique solution. This is really just an extension of some of the other existence uniqueness that we've talked about before. It's just bumping it up a dimension. Okay, so I'm not going to prove this, but just take it for it's definitely true. But the next theorem I'm going to put up here, this one we are going to prove. And this one's kind of important for where we're going to be heading to the non-homogeneous linear first order, or sorry, linear second order with constant coefficients. So here's theorem number 2. All right. And it says if y1 and y2 is a fundamental set of solutions to the corresponding homogeneous, so instead of having the F, make up a 0. So if you take that same thing, but it's homogeneous, and y1 and y2 are the fundamental set, okay, or a fundamental set, then the solution to the non-homogeneous will be y equals yp plus c1y1 plus c2y2, where yp is a specific solution here, any specific solution to the non-homogeneous. So I'll give you a second to write that down, talk a little bit about what that means. Okay, so let's break this down. So again, y1 and y2 are solutions to the homogeneous, which are going to be easier to find. Like think about what we've just been doing with the create the polynomial, find the roots and all that. We are finding solutions to the homogeneous. Okay, so you got to find a fundamental set to the homogeneous. And then we need yp, which is going to be a specific solution to the non-homogeneous. So it's going to be a function that when you put it into this differential equation gives you truth. So we call it y sub p, p for particular. So we call it a particular solution. But you find a particular solution to this, and then you just add that to the linear combination of those that were the fundamental set. Okay, so let's actually talk through the proof of this. I don't think I'm going to prove it, but let's just kind of talk through it. So think about what we're going to do. We're going to take this, we're going to differentiate second derivative and put it back in. Well, we know that differential equations are or linear differential equations are linear operators, right? Which means we can actually think about these two separately. The y particular and the C1, Y1, C2, Y2. Now, the C1, Y1, C2, Y2, when I plug those into this differential equation, are going to give me 0 because they were solutions to the homogeneous. When I put YP in, they're going to give me f of x because they are a solution to this. So when I put this entire thing in, I'm going to get f of x plus 0, which is f of x. Okay, so that's definitely true. But now the question is, okay, so what? Who cares? Well, who cares is this is going to let us find our solutions to the differential equation when they're non-homogeneous. All we have to do is find one solution. Any one, it doesn't matter. And then we can add that to the linear combination of those from the homogeneous. Okay, so think about the hard part of this. The hard part is finding that fundamental set. But that's going to be easier because it's from a homogeneous set. So let me show you what I mean. Let me show you exactly what I mean with an example. And we'll make it so that the homogeneous is actually pretty easy to solve. So let's go with this one. Let's say we've got y double prime plus 9y equals x cubed. So this is linear, second order with constant coefficients, but it's non-homogeneous. It's slightly different. So here's what we're going to do first. We're going to start by solving the homogeneous. So let's look at y double prime plus 9y equals 0. Right? So we're going to look at that corresponding homogeneous differential equation. So this is one where we're going to make our polynomial. We're going to get r squared plus 9 equals 0. So r is equal to plus or minus 3i. So that tells me that y1 is going to be cosine of 3x, and y2 is going to be sine of 3x. Remember, the real part is 0, so the e to the 0 goes away, and we're left with just the cosine and sine of the omega t, or omega x. Okay, so there are the solutions to our homogeneous. All right, so now we got to see if we can find a function that when we plug it in gives us x cubed. So how about we start here? What kind of function do you think might work there? What type of function, if we plug it into this differential equation, might give us an x cubed?
Should be a polynomial of degree 3s for sure.
That's a great idea. Let's go with a polynomial. And let's go degree 3. Because I want x cubes. I don't need anything higher. Okay, so we're going to make a guess. And here's going to be my guess. I'm going to go just generic, but I'm going to make a guess of yp equals ax cubed plus bx squared plus cx plus d. Generic third degree polynomial. Let's see if we can figure out what a, b, c, and d have to be for this to be true. So I need the second derivative. So y prime is going to be 3ax squared plus 2bx plus c. And then the second derivative is going to be 6ax plus 2b. So let me put that back in here. So I'm going to get 6ax plus 2b plus 9 times ax cubed plus bx squared plus cx plus d. And I need that to equal x cubed. All right, well, let's just lump things together by different powers. So I'm going to get 9a times x cubed plus 9b times x squared plus 6a plus c times x. That's those two. Oh, about 9c. And then for the constant bits, I'm going to get 2b plus 9d. So now let's just create our system of equations. I know that 9a has to equal 1 because there's 1x cubed. 9b is going to have to equal 0 because there are no x squareds. 6a plus 9c has to equal 0 because there are no x's. And 2b plus 9d has to equal 0, again, because there's no constant. All right, well, this is a pretty quick solve. From the first one, we're going to get a is 1/9. From the second one, we're going to get b is equal to 0. Well, if b is equal to 0, that forces d to equal 0. And if we put a equals 1/9 in here, that's going to force c to equal minus 2/27. I'll leave that to you to confirm. Okay, but all of that together now gives me a solution to the differential equation. It does give me my yp. Right? What I know is that this yp is going to equal 1/9 x cubed minus 2/27 x. If you take that function and put it in here in its second derivative, it's going to add up to x cubed. All right, so now here is my solution to this differential equation. It's going to be my particular solution. So the one that I just found, plus the linear combination of this fundamental set. And so this is going to be the general process anytime we want to solve a non-homogeneous. We're going to start by finding solutions to the homogeneous. Then we're going to have to figure out a way to find a particular solution to our non-homogeneous. And often it's guess a form. Guess a form. Look at what this is and go, what kind of function might work for that? It's not always. We're going to see that there are other techniques as well. But it's going to really come down to finding any solution. Because as soon as you find one solution, you can add that to the general linear combination of the homogeneous, and you got it. But that's what we're going to do next time. we're going to pick up this and kind of run with it and go, okay, let's start formalizing the techniques. Let's start talking about how do we go through a real systematic way so that we're not always guessing, or if we are guessing, we're at least guessing good forms. Because sometimes the forms are easy to guess. Like this was pretty clear. We have equals a polynomial, and we probably want a polynomial function. But what if that wasn't a polynomial, right? Or what if it's a polynomial, but also attached to exponentials, or, you know, so we're going to start talking about how do we break it down and be nice and systematic. All right, but like I said, we'll save that for Wednesday. Anyway, so for tonight, don't forget you have some homeworks that are due tonight at midnight, so make sure you work on those. And then other than that, I will see everybody on Wednesday. Have a good couple days.